Okay. So, hello everybody. I will share my screen with you. And I will launch. So again, don't hesitate to unmute to ask questions because I don't see you since I'm in presenting mode. And so let me know if something is unclear or if you don't hear me very well or something like that. So it's a quite long training today because it is the last training of the Genera project. And I would like to show you everything that I have developed because I think it's important that you have an overview of all the tools, what they do, and also an understanding of these tools. So before going into tools, I will start by a necessary technical background, not that much, just the necessary for you to be able to understand the infrastructure and also what are these tools, how they run it. So just a quick reminder of what is the Genera project. So Genera is the acronym of BCCM collection in the genomic era. And the objective is to establish modern genomic practice within the 5 collections that are the partners of this project: IHGM, ITM, LMG, MUCL, and ULC. The guidelines is to respect the fair practice. So everything that is developed in this project should be findable, accessible, interoperable, and reusable. That's the guideline of the development for all the tools. I would like here to mention at the beginning of the presentation the CC, who was not a member of the project at the beginning, but who helped us a lot and who actually hosts the HPC cluster that allows you to run the tool that I will show you. Finally, I will also present the different person of the Genera project because you always interact with me, but there are more than me behind. Of course, there are Pierre at the supervision and Denis also. But thanks to Loïc, Valérian, and Raphaël, we have also developed a series of algorithms that you used and that are already present in the different papers. So thanks to them. This is the Genera toolbox. I call that a toolbox because it is really what the good name, a toolbox. So the tools are developed to be able for you to be able to run omics analysis from the genome to the phylogeny and a little bit more. So you see that we have 14 topics. Each topic corresponds to one workflow that you are able to run with one command line. So you see me coming now. Of course, to run that, you will be able to connect on a HPC cluster and to write some commands. Here is just one command to be able to run that, but this is what I would like to explain you how to do that. And also after that, we will go to each tool and explaining what they do and what you can achieve with that. This is the main page of the website. So if I forgot a logo or something, don't hesitate to send me an email. So the principle behind the tools. The tools are designed as a program. It means that they are one command line, reproducible workflow. This is what we do. When you run an analysis with one of the different workflow, you have just one command line to execute everything. Here's why I'm telling you that it's present as a program. but actually it is a workflow. And there's a big difference between a workflow and a program. So when you use a program, you have an algorithm behind. So you have a reflection of within the program, let's say, like that. While the workflow is a successive step or task that are executed, and the workflow is not aware. There's no reflection in the workflow. It's just a simple execution of the task. And of course, the algorithm are the program are integrated in the workflow. But that's something that you have to keep in mind. We cannot, in a workflow, add some comprehensive way on the output of a that you can obtain. That is something that is done by an algorithm and by a program. So I just said that the FAIR principle was the guidelines, and to respect that, I choose to run Nextflow and Singularity. So I will explain first what is Singularity and then what is Nextflow, and you will more understand why it is fair. But before that, I would like to talk a little bit about our HPC cluster. So our HPC cluster is NIC5 at the University of Liège. So you can see in yellow that NIC5 is part of the CECI. CECI is, in French, is Consortium des équipements de calcul intensif. So I think in English it should be something like Consortium of Intensive Computing System or something like that. Different universities in Wallonia are part of the CECI. One of them is the University of Liège, and the cluster from University of Liège is NIC5. As a user, you will use NIC5, so you have to pass in the CECI and pass the VPN of the University of Liège. This is why you have some password to send by email and to the CG, to the CECI, and to store it. So once you are there, we will show that later, you arrive on a very big and expensive cluster, NIC5. And thanks to the grant of Genera and more, because to buy that, it's not the only grant of Genera, but with the grant of Genera, we can buy the BioQ on NIC5. This means that on this cluster that you see here, we have a disk that is specific to this project. And it's a very huge disk. You have 2 terabytes of RAM and 120 CPU. It's very recent CPU because the cluster has not much more than 1 year. So it's really a really nice machine and a chance for the project to have such amount of RAM, and because you can do whatever you want in terms of analysis. If you want to assemble the biggest genomes known, you can do that on this queue. So it's really a good thing for the project. So of course you have to connect by SSH, and I will show you that. Once you arrive, you will see something like that, and you see that you have already a series of information. We will come on that later. So I put here a series of bash commands. So bash command is what you type in your terminal. With this command, and I put what the command do here, you are able to run all the tools that I developed for the Genera project. So really, if you are able to open your computer and write an email to your colleagues, you are able to launch the tools because it's not very different. It's just a series of things to remind. You can print that page, put it somewhere, and you will always have the command that you need. So I will show you how to do that. I will show you an example. Yes. So I will come back here. So is it clear? You still hear me? It's fine. Okay. So let's go on NIC5. Let me just put that here. Okay. So you see that I tell you that you have to access to NIC5 by SSH. Once you have set up the infrastructure about VPN and SSH, and at the end of the presentation, I will show you how to do that. You just type SSH NIC5 or double click on your NIC5 icon if you are mobile external, and you will arrive on NIC5. When you are on a cluster, it is by a terminal, it is exactly the same thing as being in your document with your mouse on your own laptop. For instance, I'm on my laptop, and if I go in my document, you always have this directory. You can see that I have the same directory, and if I create one by an icon by the graphical interface, it will appear here. So it's exactly the same thing. And on NIC5, when you arrive, you are in your home. This is the information that you find here. You are in your home. You see the space that you are allowed to have in your home and the number of files that you are allowed to have in your home. I advise you to never write anything in there. Always go in the scratch directory. To do that, you have one command that is present here, cd change directory. If you change your directory to this directory called $scratch, you arrive under the place on the cluster. If you want to know which place it is, you can type pathways directory, and you can see that this is where you arrive. So this global scratch is actually a shortcut to arrive here. And of course, it is different. It will be your username. That's it. Now you are where you want to launch the tools. If you want to go, for example, list the directory that you have, you can see that ls-lrt is to list the directory by date. You can see that the last one that I create is demo or demo GDW here, or AMAO. That's the last one. Imagine that I would like to go in demo that I create for this training. Again, I list. You can see that I have a directory called work and a file called demo.nf. If I want to remove a directory, because I don't want this anymore, remove rm. Here I force the remove. And it's telling you that it doesn't work because I forgot the R, because it's a directory. Everything is indicated. So you can see that the command that you are using in bash remind what they are doing. cd change directory, pwd password directory, rm remove. That's how you can remember that. Of course, you can create a file. You can make something like, I don't know, I will create you a file. You don't need to create file when you are running the tools, but let's say that you want to create one. Imagine that you want to see this file. You can see the beginning of the file. As you have only one head, you will find only. You have one line, you will see only the line that are outputted. Instead, head gives you the 10 first line. You can also type less to see the file. So you see that is a series of commands that are really easy to understand and to run. And there's only one thing that you can do with that is play with these bash commands and to understand what they are, what they do. Now, if you want to go out, you change your directory. Point means one directory before, and you arrive here. So that's, I think, with this you can really execute the tools. Something that also you need to know is that when you are on the cluster, you use a text editor that is completely different from Office or Word that you are using with a graphical interface. It's the one that I advise you to use is Nano. So I would like to go in another demo that I made for you. Let's go in the directory, change directory to go in directory demo here. I list the file with ls-lrt, and you see all the files that I have here. Imagine that I would like to edit the job file. Is something that you will do actually for the pipeline, because it is a pipeline. You can type nano -w, always type the W, because otherwise you will lost a series of information of your line. And you can see that if I double click somewhere, it doesn't work. And I noticed from the previous training that is something that is really not well understood by the majority of the users who begin, who don't understand how to use Nano. Nano works is a colon-dependent editor. It means that it works by the arrow of your tool. You see, I put the arrow here, and it works like that. You can see my cursor in black, and it works like a color. So you cannot do any other way than type on your arrow. You have some series of shortcuts that I put you here, like go at the beginning of the line, at the end of a line, but that's. And if, for example, I want to change the number of CPU, it will be here. I can change the number of CPU from 20 to 10. And if I want to quit, it's Control X, and then I type yes. No, I would like to see if it's.
Luc, I have a question. How do you know when to change the CPU?
Yes. For most of the tool, the number of CPU are preset, so it's not important to change. But if you know, for example, that you will, for this tool is the genome downloading, that you will dereplicate the whole cyanobacteria phylum, then it's better to put more CPU. So it's really, if you make a very big analysis, that you want to change that.
So you will know the more you work with it, you will see, okay, it stopped. Maybe I can try to use more CPU. Yes. Yeah. Okay.
Yes. And by experience, you will know that if you run something, you will begin to know that this step takes a lot of time or something like that. Yeah. For example, it's also the case for the annotation pipeline, where if you put more CPU, you will stay less in the queue. And I think it's part of something that we can come back later on that. Yeah. So okay, if you want to see if the modification is done, then you see that I changed the number of CPU here, and I forgot also to change here. But we will not run that now, so it's not so important. So that's the two important part. Remind this bash command. And if I take, for instance, Elizabeth has never do that, and she is perfectly fine with running the pipeline now. So it's something that is really feasible and not very complicated. It's just that you have to pass 1 or 2 hours playing with this command and trying to launch a series of the first tool, for instance, the simplest one, Genome Downloader, and then you will understand how it works. And once you understand how works a tool, all the tool works in the same way. We will see that. So let's go a little bit further. Yes. Now that you see what is the HPC cluster, what is a text editor, what is Bash, let me show you something. If I would like to run a tool, let's say a tool that you all know, BLASTn, and I would like to see the help of BLASTn, I execute BLASTn on the cluster. Unfortunately, it is not installed. So what I would like to show you is that Singularity is for me a way to install tools for you. So you see that it's not installed on the cluster. So I will execute okay, yes. So I will execute for you one of my Singularity containers called OG-enrichment.sif. Sif is Singularity image file. And you can see that now I have the help of BLAST. That means that all the tools that are used by the workflow are installed in that way. So all the tools are present in Singularity containers. The advantage of Singularity containers is that it's pre-installed for you and it's impossible to modify. So it's unbreakable. If you want to modify this Sif file, it's impossible because when it's burned, the only thing that you can do is use it. That means that for the sustainability of the project and for the fair practice is really a good thing, because if it runs now, it will continue to run for in the future without problem. Just for your information, because you might want to know that if you collaborate with people and want to share tools, for example, all the Singularity files are deployed based on Singularity definition file called a def file. And it looks like that. You have the information of what kind of machine I would like to use, the export of the path to the tools or the program, install of the different program, and information on what you have in the Singularity. So I think we have currently 20 Singularity. I think I put 10 in the graphical abstract, which is 20. And so all the tools are deployed like that, and I store the Singularity definition file. Now that you know what is Bash, what is a text editor Nano, what is Singularity, I would like to show you what is Nextflow. You remind that I'll tell you that workflow is a series of tasks. In Nextflow, which is a way to execute these tasks, one of the way, but I think the most recent one, the tasks are called the process. And to execute task after task, you have to exchange the files that come from a task to another one. And these exchange of files are made by channel. This is why Nextflow is composed of channel and process. Each process is executed in a different directory. So I will show you that. Just know after this slide. One thing that is really cool about Nextflow is that you can, thanks to a configuration file, execute the workflow on the Singularity containers. This is why I just tell you. And within the Singularity containers, I also add a companion script who format the output to pass to each before each program, or to format the phylogenetic trees with the good names and that kind of things. And also the Python files are stored if you want to send to someone. So I would like to show you how to run Nextflow. Let's go in. So I change the directory and I would like to go in demo. So I come back one directory before and then go in demo. Is the path, and I will list all the files. One of my criticisms that I received from my previous training is that I go too fast with this. So I'll try to give you really a lot of information now, because I think it's better for you to really understand what I'm doing. So we don't need that file anymore, so I will delete it. Remember that delete is AM. I can delete the -f, and it will ask me. I know here it doesn't ask. So we delete this file. Up. And we only have one file called demo.nf. Once you see .nf at the end of a file, mean Nextflow. That means that it's the Nextflow script. Let's see how we execute that. So I will first load the module of Nextflow. But you don't have to do that because it's in the script. It's just for the demonstration. So with this command, we run the script called demo.nf, and I ask him to print me the that is running the demo. Actually, you see that the only file that we have now is demo, and if I list the directory now, we have a work directory that has been created. This is what I'm telling you here. Each task is done in a directory within the work directory that is created by Nextflow. And here you have some information, some number. It's the subdirectory and the final directory present in the work directory. So let's see what you have here. You see that is the first one. Then you have the beginning here that you can find here. This is where the analysis is actually due. And you have in this file what is run by the program. And you can see that is telling me that is running the demo, and it print me something that is called known. Why? So I would like to know, to better know what the tool do. So what I will do is Nextflow demo, and I would like to see the help. It's exactly the same thing that you will see when you will run the pipelines. And you will see that in the help, it asks me to specify a name for the name. It's optional. That means that if I don't put that, it have nothing. So this is why it print none. So let's say that I will put this option as Genera. So it will be execute. And now we can go in the work directory with this directory that you find here, not the previous one. And we can go in the point::log. And you see that now he printed Genera. So this is how you pass option to Nextflow. This is actually how you will pass option in the pipelines that we will see later. And the same thing can be executed with Singularity. So if you run this command, the same thing will be done, but this time, so with this command, we just run on NIC5. We use the operating system on NIC5, and if you add this, you run this time not on NIC5 as operating system, but you use the container as operating system. So you have all the files that are installed within this container. So this is how Nextflow works. And I think we have finished with the technical part, let's say bioinformatic part. So I don't know if you have some questions from now, if it's more or less clear.
Yes. Luc, I have a question.
Yes.
So if we want another tool to be installed, we always have to ask you. We can't do it ourselves.
Except if you can code in Nextflow, yes.
Okay.
But that's not impossible, actually.
Yeah.
But yes, I would say that from a practice way, yes, until the end of June, if you want a new tool, ask me and I will add it or create a new workflow. It depends on the nature of tools. Some workflow take 1 month to be set up, and some of them take 1 day. So it really depends on what you want.
Okay. Thanks.
So, okay, so I will continue. So you understand better when I'm telling you that you have 14 topics. Each topics represent a workflow. For each workflow, you have one command line, just as I show you, and you are able to run the analysis. I think we could say that is how to do bioinformatics with beginners, because it's the way to develop something really easy to do in bioinformatics. But I think it's actually how all bioinformaticians should work also. Having workflow for install for an analysis and develop your study with workflow is really a good way to think, because it saves your time. If you want to do the same analysis later, you don't have to rerun anything else. You just have your workflow ready. And of course, for the review, it's really more easy to have that. We just have the case for a paper with ITM. A reviewer asked us to redo the analysis with DNA instead of proteins. Okay, we run the reverse translate and the phylogenomic analysis. It takes us 2 command line, and the files and the tree were ready in 2 days. So it's really something that is also really powerful to have for a community like BCCM. And as we talk about community, something that is really useful is GitHub. So GitHub is defined, this is the advertiser of GitHub, where the world builds software, but that's really true. I think that every bioinformatician who develop codes use GitHub or GitLab, but this variant of GitHub. So I would like to ask you to create an academic account, not now, but once you will use this. So it's a new account to have with a new password, but it's really something that is really useful to interact all together. So I will show you how. Once you arrive on the GitHub of, that's not here, on the GitHub of the project, you can see that you arrive here. You have something that I just tell you before. You have the Nextflow script. You can see that you have all the Nextflow scripts here with configuration file and job file. And you have the Singularity definition file that are there. You have also the companion file that are also there. So everything that I have developed is stored here. That means that if you want to collaborate with someone, he can take the pipeline and put it on his cluster. And also, if, for instance, we have a problem with the cluster and we lost everything, with this, we can redeploy easily all the project. So here you find more information about Genera project, access to the tutorial. You have also the news, what I have installed, when you have a new version or something like that. And if you want to see what the other team do, you have the publication related to the tools and to the project. But something very interesting is the issue part and the wiki. So the wiki, we can go by there. You arrive here, it tells you how to do an issue, because it's something that is really important, but just we will come to that later. If you go on the table of contents, you have here, before tools, the 5 first is how to create an issue, and there you have how to connect on Nick5 with all the links that you need and that I will show you at the end of the presentation. And then you have all the tools. Let's see, for example, go on the first one, Genome Downloader. You have a figure that reminds you what Genome Downloader do. You have the help. I just show you how to print that in your computer by typing Nextflow Genome Downloader point minus help. But you are have also this information here, so you can go and read the same thing as would be printed on your cluster. And you have the usage. This usage is more for external user. What you are interested in is the HPC usage. So you can see that the structure of the tool is here. You have the goal, you have the help, you have the HPC usage, you have what kind of input file you need to use, you have what you have in output here, how to clean, and you have also how to cite the tool. Here you can cite OPRER, but for some of the tool you cannot cite anything because it's not published yet. And you have also the version of the program that are there. So the program use are there. So if you want to write that you use this pipeline, you can know what are used and which version to point on your paper. So that's the wiki, and we will go. The second part of the presentation is going into the 14 tools and give you a quick overview of what they do. And if you have a problem when you would like to run an analysis, you can go in this issue part. That's why it's important to create an account. Why it is more convenient to send an email? Because if you type here your issue, for example, I don't know, dump, you will have everything that is linked to FASTQ dump. So if someone has already have the same problem than you can easily know if I already solved that or already answered that to someone. Also, it installs a queue system with the issue. You see that currently we have one issue pending from Elizabeth, and the rest is a series of questions and features that I ask myself to do or that Frederick had asked me. So if you go and type a new issue, you will have 3 possibilities. You can report a bug. You can ask something, just like Elizabeth tell us how to make a new tool. Then you request that to me, or you can ask questions. So it's a way, as we are 5 teams supposed to work with this tool. It's important to have a way to centralize all this information. And I think Nextflow, GitHub is a really good way to do that. And the advantage is that it's free for academic usage. So that's really a chance, and we have to use it. So yes. So the important thing is once you connect on Genera, you're on the code part where you have all information that you can share. Issue. If you have something that is not clear, a bug, or you don't manage to run the tool, put it there. It can be something just as simple as the documentation is not clear or something like that. Any feedback is welcome. And the wiki, you can go in the tutorial. So I'll remind you there that in the wiki you have the tutorial, and don't forget here that you can see if an issue or a question has already been asked, and if not, you can type a new issue and select the one that you want to you think is the most appropriate. Yes, the structure for each tool is always the same. So we arrive at the very end of the technical part. And when you are on the cluster, is the cluster from the whole University of Liège. So you imagine that you have hundreds of users in that cluster. So if each of the user goes on the front page and begin to type, I would like to run my workflow with 20 CPU, you imagine that the cluster will very quickly die because he will not manage to do that. So everything that you launch on a cluster should pass by something that is called a scheduler, who will take the file that you send to him, called the job file. Here I call that the job file. And in this job file, you have a series of information that the scheduler will read and tell, well, you ask me this queue because you use your queue bio. You have already people who are running, so I add your job in the pending statue, and you will pass when the other one has finished. This is how we work on the HPC cluster. So for every tool, I call you about Genome Downloader, you have a series of 3 files. The Genome Downloader .nf, the Nextflow file that you will not modify because this is the code that I developed, and a config file and a job file that you will modify. I show you here the job file. A job file looks like this. You have a series of information that are Slurm specific. Slurm is the operating system of NIC 5. The OS of NIC 5 is Slurm. And you have here the real command. So for example, in Genome Downloader, the field that you have to modify is taxo level and group level. So for each job file that are pre-do for you, in the path field, this is where you have to modify. Where you have to modify. So here you don't have to modify anything, except if you want to change the CPU, and then you have to change here also. But if you want to launch it as I have pre-set for you, you always have to look in the name of field and change that. You can do that with Nano, and then you can execute this tool, this job, and the analysis will be done by the scheduler for you. I will show you a tool just after. So
sorry, Luc, Nano is active in the job file, or you must open Nano into the job file to make it work? To change
I will show
field.
you. It's better to show you. So I will show you how to launch a job. Is better. So imagine that you want to launch Genome Downloader. So you go in the wiki. You go in Genome Downloader. And here in Genome Downloader, you have the part HPC usage. You click on it, and you are in the HPC usage. There you have how to run that. So you have to create a new directory, always in the global scratch. Imagine that I would like to create a directory called demo GDB Genome Downloader. I change directory to go within that. Then I take here the suite of 3 files. So you always have the command in the GitHub. You can see that it downloads locally the 3 files that I have preset for you. One of these files is the Nextflow that you will not modify, and the other one is the Genome Downloader job. You have 2 things to modify in the genome in the Nextflow, but we will see that later. Imagine that you want to modify Genome Downloader job. You type nano, so you still don't have launched your job. And you arrive here. You remind that I'm telling you that it's cursor dependent. So you have to go with your arrow. And you don't modify anything except the field. So imagine that I want to download all genomes that are of no stock. nostoc is a genus. So I tap genus and nostoc. And I want the gene bank file, and I don't want to dereplicate, and so I also want to ignore the genome quality. Control X, yes. Now I will check my job, and you can see that I have modified only the field that I was supposed to modify. This file is ready to be launched. That's for the job file. You have another file to modify, is the config file. So in the config file, you have also something to modify, and you can see that it's still within this minus n bigger. I don't know how to say that in English, but once you have this logo, you have to modify. So I follow what is recommended. I will move the config file to something named Nextflow config. Then I will again use nano to go and modify this. Here you can see that this part called the process is specific to Nextflow. This is why I bother you with what is a process and what is a channel. So when you see process, you don't have to modify anything, and you can see that you have different process within this workflow. Each of them use sometimes a different container, sometimes the same. But you have two things to modify here. And how to know that? I just put you the command here. You have the pathway to there, and also something that is specific to NIC5 or to HPC cluster. For the security, what you have here is not actually the physical way, but the symbolic link. So you don't have to understand that. So you take just this. You still go to nano. And you can edit this part here. You register, yes, and you take the second one. And again, you edit that. And that's it. The job is ready to be launched. And the next step, once you have done that, it's telling you what you have to edit with the job, is to do sbatch genome downloader job. Sbatch is actually to send the genome downloader job to the scheduler. So I do that, and it tells me that the job has been submitted. So what will happen now is that the scheduler will read that. He will see, yes, you are on the queue bio. You want to use 20 CPU. I will look on the queue bio if I still have 20 CPU and enough RAM. If it's okay, I will put your job on the cluster, and it will execute this command. So I think that if I do execute here, this is how to see if your job is still running, and you can see that I have a job named Genome Downloader that is running. So now you understand more why I'm explaining you what is a process, what is a channel, what is a Singularity containers, how to use nano. I think that no, maybe it makes sense. I hope so. And with this process, or let's say with this way, you can launch all the tool. It's always the same. You still have three files: the Nextflow configuration file, the job file, and the Nextflow script. You change the config file to nextflow.config, and you edit the path here, and you edit the field here. So you always have two files to edit. So it takes quite amount of time to be executed. So I will show you the result because I have launched it this morning.
Sorry, Luc, you say we should know the difference between process and channels. I've seen channels on your slides, but I don't remember to have seen process.
Okay, I will. So yes, so you have the task, and actually the task is the process. So each tag that's executed, yes. This is because I think it was more easy to understand with the word task, but yes, task is a process, and each process is what is executed in the subdirectories that I show you.
Okay, thank you.
And now let's see in the result of genome DOA. So you can see that what I have executed is exactly the same command that I just showed you, nostoc and genius. And the program will create me a work directory where he will output the different process. You can see in the out file, if you go at the end, you have something like that with a V telling you that each process has been executed successfully. You have also the number of CPU hours that were used, the number when you launch it, the duration, and that kind of things. So that's something that you can check to see if everything was fine. But the most interesting part is go in genome downloader output. So each workflow will create you a directory called genome downloader output or annotation output or something like that. And then you have here, if you can sort, all the FNA is the nucleotide genome that has been downloaded. And you have also a file called genomes taxonomy, where you have the lineage of all the tools, all the genomes. So you can see that it's all nostoc.
Yeah.
It has been downloaded. First, yes.
Yeah, look, I ran it again this morning with a very small species, and the file, the taxonomy file, didn't want to open while the other files worked. So I got genomes that were downloaded, but when I tried to open the taxonomy file, it wouldn't open. So can it, I don't know what can be the cause of that.
When you say that it don't open, you try to open it how?
As I also by clicking on the file itself. So
did you try to make a less on of the file like this? So when you are on the cluster, you type less.
No, I didn't do that.
Because one thing that can happen that if you download the file locally and try to open it with I don't know your text editor, it might not recognize that it's not the good format. So maybe it's that. So try to see if a has less of or a head like this works. If it works, this means that the file is created and that you have a problem once you download it on your computer. And then we can make a short Skype to see what's going on.
Okay, I will see. Yeah.
So this is the most simple tool. So I advise you to play with that, like it's to understand the how to launch one tool and how to have how to use the Nextflow config file and how to use the job file and that kind of thing. So if something is unclear, it's good for me to know because if it's unclear for you, it's unclear for other people, and we can make the documentation better and add something, for example, an FAQ on the Git or something like that.
Sorry, a stupid question. All these downloaded genomes, where are they? On the NIC? In a certain directory or?
Yes, they are. So if you type PWD, you are on NIC 5. in the directory name demo GDW2, and within this directory. So if you want to download it on your local computer, you can use MobaXterm and refresh and simply download it. There's a part explaining how to copy files, and so the thing you need to understand is that the path is physical. That means that it's physically there on NIC5. It's exactly the same thing as if it would be on your computer. It would be something like documents slash genomes or something like that. So it's exactly the same. So yes, it's a physical point on NIC5, and so you can take it locally. Yes.
And will we continue using NIC to keep the genomes, or we will need to repatriate onto our own computers?
It's up to you. I never use the genomes on my laptop because what I do is that I give the list of the genomes that I have used to the publication in SubMat, and then I take the genome and I import it to the next workflow who use the genomes to infer orthology. So I never take that locally.
Okay.
I try to maintain that there. So you see that it's completely how to say that reproducible. Of course, here, if you run it in 1 month, you will have more genomes because it will be updated. But the work directory only contains the intermediate files, so there's no need to keep it to save the space. If you do that, you clean your working directory and you save a lot of space, and you still have the Nextflow file and the job file that are stored here, and you have the output. So really try to maintain the space because it goes fast to lose the usage of a computer because we don't manage correctly the space. So that's it for the demonstration, let's say the technical demonstration. So before going to the tool, so I will make a short summary. What is important is that you remind that you use NIC5 in the global scratch directory. You have to remind with the bash commands. You have to put that a little bit in your mind by trying to play with this. And then once you launch an analysis, you have 3 files. You remind that, and I think you are ready to launch the tools. So let's go now in the different tools. The first one, we just play with it, but I will nevertheless speak a little bit about it. So in yellow, for all the tools, you will find a figure like that. So in yellow is what is mandatory, so what will always be run by the tools, and in green, what is optional. For example, here you can see that you will always download the RefSec genomes. That's the first things to do is download the RefSec genome. An option is to add the GenBank genome. And at the end, if you have an ID of a genome already present in RefSec, it will not be downloaded in GenBank. GenBank is complementary from RefSec. So first RefSec, and you can complete RefSec by adding GenBank if you want. Then at the end of this step, you can, if you want, dereplicate genome. The replication is made by DREP, which is the most known software for dereplicate genome, and it used the genetic distance between pairwise association of genome to dereplicate and not output you the genome that are to output you only the genome that are the most representative. So it permits you to decrease the number of genome, for example, if you download the whole film or something like that.
Sorry, is it 100% or you can say I dereplicate at 95 or something like that?
No, it's prefixed in, but it's not an average nucleotide identity. It uses MASH, not INI. So the threshold are a little bit different. But here the threshold is fixed in the rep. But you can, I think I can add a threshold, and that is grossly yes. You can say 95% or something like that. So it can be an option to add. Currently, I think it's 95%.
I don't insist, but I'm just curious to know what is considered identical genomes that you have to.
Yes, that's the best things would be to try different tools and to, for instance, try to compare with any. But currently, yes, it's prefixed, so it's the default threshold of DREP, because from my usage, once you want to, so all the workflow of Genera are designed phylogeny to help the taxonomy, and in that way, the DREP threshold was always the good things to do. But we can set up the different MASH thresholds, and one thing that you will do is run the different phylogeny with different threshold of MASH. That's something that you can do. For me, it's adding the threshold is just a 2-minute modification. So that's a bit, but I don't have the expertise on what would be the impact of that, and what is the difference between MASH threshold that is used by DREP and the INI threshold. We have also another tool that I plan to add to this is Torquemada, made by Raphaël and Denis at Liège, who have more than MASH. They have MASH and ANE, and it will be more easy to compare. And you can set the threshold more easily with Torquemada than with DREP. But currently it's not installed. It's also why I don't install a threshold for DREP. I would say that DREP is temporary. It's something to release the tool so that people can use it. But the future of that is to add Torquemada into this genome downloader.
Okay. Thank you.
Yes, for all tools, I will show you the help. So the group is the group of interest. So group is this is the help. So you can see that ref group in the group is cyanobacteria, and cyanobacteria is a phylum. So this is the only two mandatory argument that you are forced to use. But you can also, for example, specify a tax dump, even if it's already set. Jimbang is can be activated or not. It's the same for DREP. And something that is great is once you run DREP, you can set up the genome quality, and the genome will pass a CheckM contamination detection before being downloaded. So you can decrease the contamination, genomic contamination, while doing this genome quality by activating that. I already show you the output of genome downloader, so we will not go in detail of that. You see that it's for trichophyton, so it can work for eukaryotic genomes and also for prokaryotic genomes. Another tool, the next one in the line of tool, is Genome-assembly. So first I will give a little introduction. So once you want to assemble a genome, what I say assembly is going from the raw read to the contigs. And if you want to go further, is to try to separate these contigs into metagenomic bins, so into individual organisms by binning, metagenomic binning. The reads can be Illumina short reads. So I remind you that Illumina is short but with a high accuracy, while long reads, NanoPore or PacBio, are long but with low accuracy, at the exception of the very recent PacBio Hi-Fi reads that are not included in the Genome-assembly yet, because we don't have Hi-Fi to test the tool. So Hi-Fi is quite expensive, and so we cannot do that currently. But if one of you possess Hi-Fi, I would be happy to incorporate that. So you will see that it is a little bit more complicated in terms of pipeline than the genome assembler, than the genome downloader. So the first step, so you can see that it can take short reads or long reads, so PacBio or NanoPore. The first step is trim the short reads. It's done with FastPay, so you don't have to pass after FastPay because FastPay is quite efficient in terms of streaming and cleaning. But I also add a FastQC of the output if you want to see what FastPay has done. The genome assembly can be done in two ways, in terms of pure genome or in terms of metagenomes. So if you think that there's a chance that your genome is not, that your sample is not completely clean, I advise you to go for the metagenome option. In red is the short reads, you can see. So for the short reads, it's always space that is used. And for the long reads, you can use Fly or Canoe. For the metagenome pipeline, Fly is the only long read assembler able to make a metagenome. So it's just the only one that is possible to use. For long reads, in blue, we use the short read trimmed to polish, so to correct the error that can be persistent in the genome due to error in the long reads. Then we do a read mapping for the binning. So if you don't use the binning, if you use the genome, you will skip this step, and you will also skip the binning step and go immediately to quality estimation. But if you use the metagenome, it's a little bit more complicated. And the binning in metagenome is made by coverage of short reads, not using the long reads, because as the long reads has error in it, if you try to map it on the genome and try to bin, the results are less convincing than with short reads. I tried the two, and currently the only possible option in genome assembly is to use the short reads for mapping. You can do a scaffolding. So I tell you that here you can go to contigs, but you can also do to scaffolds. And the scaffolding is made by Ragtag. Ragtag is the new, for EHM people, the new version of Ragu that we use in the paper. So if you have a reference genome, it will order your contigs present there according to this reference genome. It will not correct your contigs. It's a possibility to correct your contigs according to the reference genome, but currently I just use the option of Ragtag that organize and scaffold. And of course, you have the classical quality estimation with Quast. For all the tools in the figure, you have here the golden rules that remind you how to run the tools. Create a directory, download the assembly.nf, download the assembly.config and transform it in Nextflow from config, edit the binding section, then edit the job with the fields, and then submit your job. So if you look at that, if you don't remind after a series of time because you don't use it. It gives you a quick overview. This is the help of the assembly. You can see that the only monetary argument is short reads, because by default, if you don't provide long reads, it will think that is a short read assembly. And if you provide long reads, it will activate the long reads. You can also specify long read assembler. By default is fly, but you can also use canu only if you don't run the metagenomic mode. And you have the different options like the RAM, the CPU, the reference genome if you use ragtag, and also the binner. By default, it's none because binner is not activated. You can activate the metagenome without activate the binning. That's a possibility. But if you want, you can type all or metabat or concoct. It's the only two that I use currently. Why metabat and concoct? Because metabat is more oriented on bacteria, while concoct is not preset for an organism and can be used also for eukaryote. One thing that you have to know is that if you activate the metagenomes, and especially the binner, on an eukaryotic genome, you have a high chance of loss of mitochondria and plastids, who are recognized as bacteria, actually. And so you will always have different bins and who are difficult to identify. So let's go to show you how it looks like on the cluster. So that's an output of the program. I will go and show you what kind of output you have. You always have a file called log. It tells you what has been done by the pipeline. So if you store that, you always have an ID of what has been done. And also I compute the binning. You can see that metabat bin nearly all the genome in terms of length, but it represents only 10% of the contigs, while it's completely bin by concoct. So you see that there's a gap between probably a short series of short contigs due to the metagenomic way activated. And you also have the version of the pipeline. So once I update the tool, this will be updated, and the old version, so for example here, the first one, will be stored, and I will make an archive of that. So that means that if you want, after 2 years, to know exactly the version that you would like that you use in the pipeline and see, have a look at the codes or something like that, you have it in your local directory, but I will also store it. And you have the different bins that were computed by concoct or by metabat. You have the fastQC. You have information about the short read coverage. You have it's computed by, I think it's metabat here, and you see that the total average depth is the third column. So you see for the contigs, the average depth in terms of Illumina, you can see that it's between 60 and 94. So it's quite a good coverage in terms of Illumina. And you have the same thing for long reads also. We have the coverage, and now it's this column, and you can see that the coverage is 100 at maximum, but always close to 100. So it's also very good coverage in terms of long reads. And you have the genome here. The genome is always named genome, even if it's a metagenome. So it's up to you to know what you have launched. So here you have the genome, and that's the genome produced, and you can see that it's polished by the pipeline. And if you assemble by pure way, so no metagenomic, these concoct and metabat will be present also, the one bin, and in the file you will have information like metagenomic mode not activated. So you always have the information. And of course, you have also the QAS results. Here you have the QAS result for all the for all the bin, and also for the genomes somewhere in the file. So that's also something that you can output. I think that's it for Genome Assembler. So if you have questions, don't hesitate. It's really a pretty useful pipeline. I already use it a series of times, notably for MUSQL assemblies. And it's pretty straightforward. Yes?
When will the recording be available?
What do you say by recording?
Yeah, of the training here.
I think it will be by the end of this week.
Yeah, okay. Because there's a lot of interesting information that is set.
Yes, I know.
As a help when we combine it with the GitHub information, it will help a lot.
Yes, so that's why I register it, because it's more easy for you to come back later. And I will also put a timestamp between the different sections, so you can go by clicking immediately on Genome-assembly or in Genera infrastructure or what is Nextflow. If you have the different topic, I will do that this week.
Okay, thank you.
Nick?
Mm-hmm.
You speak about a reference genome on which you can map the reads. This genome, you can input it yourself, or it is automatic?
Yes, you. No, you have to, as it's a single genome, you can download it from the NCBI, for instance, and provide the genome. Something that can be done quite easily is also to just put the GCA number. That's also something that I would like to add. So just put the GCA and the download is automatic. Currently, it's not activate that option. But yes, you have to be sure that this genome is so nothing in your genome assembly will be modified according to this option. So you will not incorporate genomic contamination or error of assembly, because you simply order the config. If you have a good genome, you have a good reference genome. For example, if you work on a plant and you want to order according to Arabidopsis or something like that, that would be perfect. Or if you have a good cyanobacteria, I don't know, maybe Acariocoris or something like that, that would be fine. But you have to look also on this. Why I don't activate the automatic download, because you have to look on the NCBI metadata and see the technology of the genome. Is it a long read genomes? How many contigs do you have? And that's also a way to see this ragtag possibility.
But at the end, it's a personal choice.
Yes, exactly. I think it's very useful if you are sure that the reference genome is fine. And if you use long reads, I'm not sure that this option is useful anyway, because you already have a good contiguity and that kind of things. Okay, so I will switch on the next one, who is Genome-quality. Fascinating topic. Huh? I like it a lot. You know that. This is the potential genomic contamination. So that's really what I do on my free time, let's say. When you have your genome, you have plenty of to make it bad. The contaminations can come from everywhere. Here you have a series of sources of contamination. I will not cite it all, but what is important to understand is the center of the figure here, the redundant contamination and the non-redundant contamination. When it's redundant, imagine that you have a protein that is, or a gene, that is already present in your genome. And then you will collect the same gene, the ortholog gene, from another organism, and you will add it into your genome. That's the redundant contamination because you have 2 times the genes, 2 times or 3 times or 4 times the gene. The non-redundant contamination is where this gene is not present in your genome, but replaced by the gene from another organism, or you had a gene that is not ortholog at all in your genome. So at the end, what you can have is redundant contamination and non-redundant contamination. So that's really important to understand that. And this can be found in all databases, including RefSeq. When you download the genome, you have to look on the genomic contamination. And you have to look for redundant and non-redundant. Here it is a summary of all the tools that are used for genomic contamination detection. Here on the left, you have the tools that are not related to database. It's really a remarkable and interesting tool because you are not linked to a database that can be contaminated also. But this tool requires a user interaction for each genome. It's genome per genome. So imagine that you want to download the whole Cyanobacteria phylum or the whole Proteobacteria phylum. You will not go genome per genome. So I will not add these tools in the Genera workflow. But it's good to know that they exist. And if you have a specific problem, then maybe you have to come back to me with the genome. Then you have the genome that are based on gene markers for linked to a reference database, and those who are genome-wide. The biggest difference with that is when you have a gene marker, is the genome is reduced to a series of genes that are the gene markers, and the program look if you have these genes more than one time. So clearly it is oriented to redundant contamination, while when it's genome-wide, you can also include non-redundant contamination. And within this technology, you have different possibility of sub-technology, let's say like that. For example, in gene marker, you can use only one is the SSU RNA gene, one gene, or you can be multiple locus. It can be only on ribosomal protein, or it can be a phylogenetic placement. So the most used tool for bacteria is CheckM, who is very close of Busco in terms of result and technology. I include the two in the workflow that I will show you, because they are based on one of these technologies. And I also include some of the genome-wide. GENC is one of the latest one, who use chimerism of contigs to detect genomic contamination. And the conclusion of the author of GENC is that it is not for some case, let's say, for example, when it comes to species contamination with the same species or close contamination, you have to use a corroboration between GENC and CheckM. So no tools can detect all contamination currently. This is why what I see when I do my test. you have to use the two. So if you want to decontaminate bacterial genome, you have to run gunc plus checkm. I also add Physeter, the tool that I developed with Valérian and Denis, with complementary, because it's a genome-wide approach based on last common ancestor, and who can work on eukaryote and prokaryote, while gunc and checkm work only on prokaryotic genomes. And finally, I also add Kraken, because Kraken is one of the most known software in metagenomics. It works very well, probably one of the most reliable if your genome is known and if your contamination is known. So if it's present in the database. Why? Because Kraken rely on exact K-mer matching. So that means that it will look for short region of DNA, and this should be exactly the same. It's an exact matcher. So if you have a divergent genome with some mismatch comparing to the Kraken reference database, then you will pass in terms of unknown. This is why a combination of Kraken and Physeter is useful. This is the only tool that I have currently add. So checkm, Busco, gunc, Physeter, and Kraken. If you think that you need more, please tell me. So we write, it's not easy to give you this introduction to genome contamination in 10 minutes, but we have write review with Denis on this topic. And so you can read it, and you have these two figures and with all the explanation of what each tool do and what are the advantage and disadvantage of each tool. So if you think that you have, let's say, a study that falls outside of the checkm, gunc, Kraken, Physeter, and Busco space, then contact me and I will add something more. So this is what the tool do. It's a tool designed to be completely exportable. So all the database and the taxonomy setup for all the tools is automatically deployed. If you run somewhere else on another cluster, but you have the database on NIC5 in a shared folder. And then you can run all the tools, or you can run only one. And you can see that the very last one, Quast, is also a way to estimate the quality of a genome. If you have some doubt of your genome, you can corroborate the result of your contamination detection with Quast. If you have a short amount of contigs, then probably your genome is more clean than if you have a lot of contigs. And you also have the possibility to print a final table, positive table, with the tool that pass the different threshold. It will be more easy to understand with this. That's the help. So the only thing you have to provide by default is a directory named genomes with a genome named genera-input, sorry. So you put all your genomes with the extension .fna in the genera-input. And then it will run by default all tools. But you can also specify which mode you want. And for Kraken and Physeter, you can specify the taxonomic level. By default is the phylum, but you can go to the species level. And the final list is the threshold that you can set up to print your final list. So I will give you an overview of the result. Here you have the different results. You see that none of the genome pass the threshold, because I put really a hard threshold to test that everything works fine. But you have a final table. I don't know where it is. Yes, GENERA-content table. And you have all, you can see here that you have all the, you can open that in Excel, and you have all the all the information output by all the tools. And you can also go, for example, in checkm results and see the different results for each of the tools. And that's it for the genome quality. I don't know if you have any questions.
Yeah, sorry, because I had to discuss with the team. On which genome did you do this? Is it the no-stock genomes? No.
No, it's a series of genome that I have built to test the tools. So it's a genome with a preset level of contamination to be sure that everything works fine.
Ah, yeah, okay. Thanks.
Yes. I also tried with the no-stock, and the result was so bad that I quit. Okay, maybe we can make a 5-minute break so I can take a coffee and come back in 5 minutes.
Yes.
Okay, so let's see in 5 minutes. Okay, can we start again? I don't know if someone is there or not.
Yes.
Yes, yes.
I'm here.
Okay. So let's go to the next tool. So yes, this is the annotation. As so all the other tools were built on Singularity plus Nextflow, but this one is actually built only on Singularity because it was impossible to pass AMAO in Nextflow. So the prokaryote way is pretty straightforward, it's prodigal, and I plan to add also proca because proca gives you, it's more recent and give you a better, it predicts already all the ribosomal proteins and annotate already a little bit your genome. So I will add proca, and you will have the choice between prodigal and proca.
Okay.
But AMAO is for eukaryote. So prediction is in eukaryotic genome is much more complicated than in prokaryote, of course. And it's an integration of a series of tools, Maker, Augustus, Trinity. And the integration of these different steps is really complicated. I think with Loic, we made something like 1 year to put the Singularity container of AMAO ready, because there's always a library who will miss or something like that. It was a headache. And unfortunately, it's impossible to pass it in Nextflow. So you will have to use it in the command line, but it's only one command line also. So the command line should look something like that. Maybe I will go within the here's it will be more easy to see. So if you go in annotation, you find the same figure. So you have the help of prodigal and of AMAO, and you have how to run it. So you see the number of possibility of AMAO. That's a lot, but it's preset by default. So what you have to do is this. So you call the AMAO file, and you put your genome, the name of your genome. So here it will be only the name of your genome, and then the only thing that you have to do is to type the name of your species. By default, AMAO will look into on the NCBI to download RNA-seq data for you, compile it, and so assemble it with Trinity. And this evidence will be used to train the model of Augustus. And if you, that's what happened if you put EST1, and if you add protein 1, it will go it will download also the proteins that are already present on the NCBI and use it also to train Maker. You have the set of CPU, but you don't have to modify that, and the output also don't have to be modified. This directory is a directory that you don't have also to modify because it's a database used for AMAO. So everything is also pre-defined in a directory, in a job. So if you go in your directory, let's say we can do that here. That's not the good orthograph, but it's not problematic. And you do that. What you will have is two files, one file named proca and one file named EK. Take the one that is convenient to you. And if you go in EK, what you will have is the same thing that I just showed you. So modify your genome, field 2, field 3, the organism. Your organism should be with an underscore between the genus and the species as it is shown on the NCBI. And the field here is the pathway, local pathway that you can obtain with this. Everything is written here in the job file. If you want to know if you have already RNA-seq data and how many RNA-seq data you have, you can make a query like that, and it will explain you what AMAO do. You can see, for example, that you have one SRA for the test that we used with Loic, Uroleptis citrina, and you see that we have an underscore, and the query on the NCBI is with n RNA-seq. We do that remotely, and this SRA file will be downloaded and assembled for AMAO. It's the same thing for the proteins, but with the other to the link. You don't have to put RNA-seq, but proto, something like that. You can also specify the Augustus gene model, but that's not mandatory. And I think.
So in this, for the prokaryotes, you don't need to put a field.
No. In prokaryotes, it's more easy.
To say
only the
which
genome.
organism.
No, not for prokaryote. You just put the name of your file. So it would be, for example, the name before your FNA. So imagine that you download, you have assembled a metagenomic bin called concoct bin1.fna. It will be concoct bin1 dans all field 2. And it's also the same for procar. So it's not dependent of the name of your organism. So the prediction is always the same. So here procar, I will not show you because it's for the prokaryote, I will not show you because it's really easy to run. And also, I'm not sure that you will run it because Prodigal is already integrated in all the rest of the pipeline. So you will not have to run it. It's just if you want to have your protein predicted and have a look on that. But the orthology step will already do that for you. Will already do the annotation. But for your eukaryote, you have to run it before. AMAO is very useful for non-model organism because for non-model organism, it's not easy to find the RNA-seq data or protein file, and this is why AMAO is useful. If you have a model organism, then probably it's better to use Bracker2, and I also plan to add it. But Bracker is not so easy to use as AMAO because you have to point specifically on the protein and point specifically on the RNA-seq data. And it's also very difficult to install. So currently, I think it's better to use AMAO for all annotation, especially for the organism that you work on at BCCM collections. So that's for the tool annotation. And yes, if you go for eukaryote, you have a series of files that are not that are useful for a publication that a reviewer might ask you. But what you are interested in is this final protein file called Augustus protein. No, I think it's yes, it's this one. This one is the one that you are looking for. So these proteins for eukaryote or for prokaryote can be used in the next tool, who is Orthology. So Orthology is also a quite big workflow. So Orthology will go from proteome, but at the beginning, if you work on prokaryote, you can tell it to the workflow, to Orthology workflow, and it will run Prodigal to have the proteome from your genome. It infers orthologous gene, and the last step is to infer core genes and specific genes. So I will explain you what is core gene and what is specific genes. So core genes, when you run the orthology, is to avoid paralogy in your phylogenomic analysis that can ruin your analysis. But if you want to exclude xenolog, you would like to, so the lateral gene transfer, you would like to have the core genes, so the genes that are shared by a series of organisms and that you are sure or pretty sure, let's say that you don't have xenology within it. And a specific gene is at a different taxonomic level. So core genes, I will explain you specific gene just at the year after, but core genes in the orthology workflow are defined as genes that are shared by all genomes. So you can you must specify a list of organisms to consider for the core genes, and the program will look if your if all the organism from your list is present in your core genes, but in unicopy. That means that if you have someone else in the gene, so imagine that you have 10 species, 10 proteome at the beginning, and you add 8 only in your list. If we have one of the two remaining sequence from the two remaining proteome within the gene, it will not be considered as core. So it's only the member of the list, and this member of the list must be unicopy. That's how I define core genes. Of course, it's very stringent, and you can have housekeeping gene within these core genes. While the specific gene list, well, the specific gene is at another taxonomic level. That's a figure from the paper on Snodgrass-Ella. If, for example, you have different set of species that we define here in different color, and you want to know the genes that are specific to this, for example, Apis group 1, what you will do is that you will put these 3 species of Apis group 1 in the list and not this one. And the specific gene will be, as for the core genes, the genes that are present at 100% in, so you must have the 3 species here in the file, but not more. And these species should be also in unicopy. That's the specific gene. So it's like a core gene, but at another level. And also we have a pipeline at the end to give you the function of the different genes. I will show you that later. That's how orthology works. So don't worry about taxonomy and format. It's an automatic setup. You can specify it, but it's an automatic setup. If it's nucleotide, it will run prodigal. If not, you will have to provide the proteins, if it's, for example, an eukaryote. Then the orthology inference can be done by 2 ways. OrthoFinder, which is the latest and most used orthology inference program, or it can be done by OrthoMCL while using the pangenomic mode of Envio. OrthoMCL is more ancient, and you have to specify his prefix by Envio, but you can also specify it. You have a threshold of to define the orthology, and so with this threshold you can have more or less paralog in the orthologous groups. So why I use Envio? Because Envio has a geometric and functional index, which can make this inference of core genes and specific genes better, because the geometric index is structural. That means that you don't have, if you have too many gaps in your alignment of genes, it will be discarded. And functional is a conserved pattern of amino acid. That means that if the gene is too divergent in terms of functionality, it will also be discarded. That means that it's another level of to define the core genes. But you can do the same with OrthoFinder if you don't want to use the geometric and functional index. And for eukaryote, it's not possible to use Envio, you have to use OrthoFinder. Of course, you have to provide a list for the core genes, but also for the specific genes. Something that I add for the Snodgrass paper is in the specific genes, as Envio has a threshold of orthology inference, instead of asking immediately when I look for the specific gene, maybe I have to accept someone, yes. Instead of asking immediately for the 100% of presence, I ask 60% of presence. So for example, what you will have here is to be present in the specific gene list, you have to have 2 of these 3 species. But after, at the end, I perform an orthologous enrichment in Envio with all the species present in the orthology inference. So the genes defined by the presence of 2 and only 2 of these organisms from the tree here will be orthologous, will be enriched by an orthologous enrichment with all the proteome from this list. And at the end, I will only take the one with the presence of the tree 100% without presence of any of the other ones. So it's a double control on the orthologous enrichment on the specific gene content. That's not present for core genes. That's only for specific genes. So at the end, you can be sure that the genes that are targeted as specific are only found in your genome or in your proteome. So as this command can be quite long, so you should provide an in files, a directory code in file with the nucleotide or the proteins. And you should also specify if you use nucleotide and proteins. If you, for example, try to provide nucleotide with eukaryote, you will have an error because prodigal will fail because it's eukaryote. So you have to be aware of what you are doing. You can activate Envio, which is deactivated by default. So by default is it's OrthoFinder who run. Of course, you can specify that you want to activate the core option, but you have to specify a core list. And you can also specify the specific option, and you have to provide a specific list. And the 3 last ones are preset by default. It's just for you if you want to use a specific tax dump or something. Let's see how it looks like. So you have to think that in 2 times. The first things to do is to have a phylogeny, to know what are the species that are linked to run the specific gene. Or you know before running that because your species is close in terms of average nucleotide identity, or because you have a previous analysis that, or you have, for example, you want to know even if the species are not related, but you can take species that have the same way of life without being related in terms of phylogeny. And you can also try to specify the specific gene content and see what you have in common between them. So this is how it looks like. You see that I didn't clean the work directory for the majority of that. It's because it's the test. So what I'm showing you is the test file for all the workflow. So I keep it because if you have an error, I can already run it. I can rerun it that and see in my output how it looks like. So you can see that the job file is long because I have a directory called infile. I ask the mode inference because I don't have the orthologous group. You can also specify, you can also provide the orthologous group immediately. So for example, if you want to run the specific gene a second time, you don't have to rerun the orthology. You can just give the output of the pipeline, but here it's not the cases. I run as inference. I activate the core with the core list. I activate the specific option with the specific list with Envio in terms of nucleotide and 20 CPU. What I have is a directory called Genera-Orthology. As always, I have the log, who tells me what I have here. You have here the number of core genes. So you see that the number of core genes here is quite limited. And you have everything that you can see that it's the second version of Orthology already. You have here directory of name Envio pangenomic files that you will have to provide if you run the specific gene after. And then you have a directory with core genes, a directory with specific genes, and a directory with all the orthologous genes that you can also provide if you run a second time the pipeline. So that's how Orthology looks like. I think it's all for Orthology, yes. So at the end of Orthology, what you have is the basis of your phylogenomic analysis because you have your orthologous groups. So you can see that either you provide your proteome if you are work on eukaryote with AMAO, predict with AMAO, and if not, you use immediately the genomes, and in one single command you have the OGs with your core genes. Usually, I use the core genes in phylogeny analysis, and you will see that in the phylogeny analysis you have different degree of corroboration, and if you have a problem with this corroboration in your analysis, then you have to come back to the orthology inference and try to understand if you don't have strange signal or something like that. But from what I have seen in the topic of study, the phylogeny used by BCCM are not conflictual and difficult phylogenetic question, but more oriented on helping the taxonomy of something that is quite easy to do. So the pipeline that I developed here were sufficient until now, but maybe in the future you will have another situation, put an issue on the Git, and we try to solve that. Okay.
Yes, Luc, I talked with Benoit because he discussed with you about this analysis with the cyanobiome genomes of the collection.
Mm-hmm.
And
yes,
it
yes.
was very positive, and hope that he can collaborate on that.
Yes, he sent me an email. Yes, I asked him to discuss with you to see if you agree with that.
Yeah, of course. Yeah.
The objective that Benoit would like to do is to use only Genera to make the whole pipeline. And the question is very interesting because he has different synobium. I'm not sure about the phylogenetic position, so that can be we see where they come in the tree, and also how they are phylogenetically related to run the single gene content.
Yeah, they are related. Yeah, polar.
And so that's very interesting to know.
It's a group of polar strains, Arctic, Antarctic, and a few or one Belgian.
Yeah, for example, you can make what are the genes are specific to Antarctic, the genes that are specific to Arctic. Do we have genes that are in common? And that's already something interesting to know. And what are the functions of these genes? Do we have genes that are related to something like cold resistance or something like that?
Yes, yeah, polysaccharides and something like that, or stress.
Yes, we already begin to work on that, and Benoit already found a series of bugs in the tool, so it's my beta tester. Yes, I try to make a lot of tests, but of course for the majority of the tool, the naming of the file are very important. So if you name your file in a strange way, if you have a series of minus or very long names, then it can crash the pipeline. This is what happens with Benoit, and so we already modified that, and we plan to discuss shortly to finish that.
Yeah, nice.
Yes, the reverse translate, that's it's a very simple tool. Once you have your orthologous groups, they are in proteins, and for most of the phylogeny that are related to closely related species, it's better to run it in protein but also in DNA. And so reverse translate will take your orthologous groups and reverse translate in DNA. The interesting things is that it will keep the alignment of your proteins, and so you don't have to realign your DNA after. You can see that it's very easy to run. You only have to provide a directory with your orthologous groups and a bank with your genomes, and then you run it in one command. I can show you how it looks like. So, for example, you have the orthologous groups that are here. Here they are not aligned, so you can activate an alignment, or you can not activate. If your orthologous group are already aligned, you don't have to activate the alignment. And what you will have in output is a directory called DNA with the same but in point FNA, and as always, the log of the workflow who tells you what has been done. And if we have a look at the job, you can see that the directory OG is named OGs, like my directory here. And I have also a directory called bank for the option bank. And that's all. So it's a very simple workflow, but very useful. In the same way, you might want to perform the orthologous enrichment. So if you remember, to check the specific genes, I perform an orthologous enrichment. But once you have your specific gene or your core genes, for example, you might want to try to enrich these orthologous groups with genomes that were not present in your orthology at first. That's what the tool Orthologous-enrichment do. You can enrich protein file or DNA file. I will show you how it looks like because it's also very easy. So it's not important to make you an extensive background on that. You can see that the command line, as for the previous one, I provide my orthologous groups. I also provide a directory named representative and also a directory named org. Org is the organism to add. So imagine that you have a cyanobiome and then you want to add the nostoc that APOLAR to see if you can add on your core genes. It should not, but let's say the nostoc were not present in your orthology inference at the beginning and you want to check. What you will put in org is your organism. So let's have a look in org. Okay. It's the genome in terms of nucleotide. Now, in the representative, it's in your alignment. Imagine that you have 10 cyanobiome. You should at least provide 2 or 3 cyanobiome that will be used to blast the new organism on the representative to see if you have to add it or not in the orthologous groups. And at the end, what you will obtain is the log and the directory remain enriched with the tool, with the orthologous group enriched. So that's also, as for reverse translate, is also something that is very useful. So these two tools, reverse translate and Orthologous-enrichment, use biome score developed by Denis Bourrin, and only that. Then the next tool is the phylogenomics pipeline. So the phylogenomics is multi-locus maximum likelihood phylogenomic. Here I don't integrate Bayesian phylogeny, but only maximum likelihood, because until now all the phylogeny were easy to produce with maximum likelihood and with a corroboration between the different tests that I will show you. But if something more complicated comes in the future, we might add the Bayesian possibility on that. There's two ways to perform the phylogenomics. The first way that I present here is from the orthologous group perform single gene inferences, and then to make a consensus between these three. That's the supertree method. The other way is to concatenate all the orthologous group into one supermatrix and to infer the tree from this supermatrix. That's the supermatrix method. I only integrate the supermatrix method. So you can see that phylogenomics is here in the genera a maximum likelihood. So we left the Bayesian method for later, and it's only take supermatrix and not the supertree. So there's also a place to make this workflow bigger and maybe integrate more possibility to resolve complex phylogenetic question. And again, in the supermatrix, in the maximum likelihood, we run only RAXML as a tool, which has a limited set of options also. One possibility would be to include IQ3, but again, until now, everything works fine on the question that we take with RAXML. So that's the pipeline. So you can see that this is also a bigger one. Don't worry about the format of orthologous groups. It's because the naming of the group made by OrthoFinder or Envio are not the one that are taken by. So I changed that, but it's rechanged at the end, and so don't worry. The first step is to perform an alignment if your orthologous group are not aligned. For the DNA, it's not an option because as it comes from reverse translate workflow, they are already aligned thanks to the protein alignment. Never try to align the DNA because the phylogeny use the codon position. So if you try to align, you will switch the phase and you will completely mess up your phylogenomic analysis. Again, the unambiguous position selection is not set for DNA for the same reasons. It's only available for protein. At the end of that, you arrive with a series of orthologous groups that will be used for two kinds of assessment of your phylogeny. The bootstrap method is the most well-known. You take all the genes, let's say all the core genes, you make a concatenation of them, and then you run immediately your maximum likelihood inference on this concatenation. The specificity of this workflow is that for the DNA, for protein, it runs immediately one single analysis, but for DNA, you have three. You have no partition using all the sequence, using the codon 1 and 2 only, or using a specific partition for codon 1 and 2 and another partition for codon 3. That's the three way to perform the analysis. It would be logical that without partition it fails, but it fails, not fails, but that the result is not logical. But the result for codon 1 and 2 and a partition on codon 3 should be the same, and the protein also. That's the bootstrap. The jackknife is slightly different. you take a pool of your orthologous group, and from randomly you select a series of them, a subsample of them, and you make a concatenation. Then you, instead of running one protein, 1 ml analysis, you run, for example, 100 analysis on 100 concatenation of randomly selected orthologous groups. Again, the tree one for DNA. And on this 100 concatenation, you make a consensus of the tree. That's the jackknife method. So what I advise you to do, as is already quite strong, is use the core genes, make a bootstrap and jackknife together in protein, and bootstrap and jackknife in DNA, and the result from your jackknife in protein, bootstrap in protein, and jackknife in DNA, the two there, and the two there in terms of bootstrap should be the same background, should have the same background. That's how I see the corroboration in phylogenomics. If your tree is well resolved there, I think you have no chance to have a false phylogenomic results. Of course, if you have a problem there, then you have to come back to Denis or to me and to see what happened. But if the result is consistent here, that's a good signal, and I think that you can publish your analysis. You can see that even if the pipeline is quite complicated, you only have the path to the orthologous group as mandatory argument and the path to the EDM file. We will show that. I will show you that in the on here. So Orthology, multilocus, maximum likelihood phylogeny. You see that is the same image. And in the input files, the orthologous group will have this, will look like that. So each def line, you have a name of your genome, an arrow base, and something after, whatever it is. In the EDM file, this name that you find here should be on the second column and should have a longer name before and a tabulation separating the two columns. And you also need to add these two TS. With this, once your analysis is done in the tree, the workflow will replace this by this. So you have an already completely formatted tree that you can export, for example, in ITOL or in Figtree, and that you can already put in forms or in figure. So I will now show you. So you can see that you can activate, you can specify the mode. By default is protein mode. You can specify if you want to activate the jackknife. By default it's not. And when you activate a jackknife, you should specify the number of replicate and the width of the replicate. So it's a matrix, a super matrix. So if you want 100 super matrix is the number of replicates, and the width is the width of the super matrix. It's in terms of position of course it's DNA. You will have more position than if it's protein, but it's up to you to specify this. By default is 100,000, and also the number of CPU that is preset in the results in the job file. And so what you have at the end is the log, as always. I will show you, and then you will always have all these files. Of course, if you run the protein mode, all the DNA file will have a message like DNA was not activated. And they are already formatted according to the EDM that you provide. So I will show you that. You see that my job is there. I run it on 20 CPU. I provide a file EDM, and my orthologous group was in DNA. This is why I activate the mode DNA. And if I go and look at the file EDM, you see that it's the name that are present in my orthologous group and the name that I want to be present in my trees. And if you go there, you have a log as always, telling you everything that has been done. And I see that the version is lacking, but it is because it's the old version of an old result of phylogeny. The version is now indicated. And you have the tree that are present there. It was in DNA. And you can see that the name that I put in my EDM has replaced the name of my orthologous groups. And that can be already exported. And that's it for the phylogenomics part. No, I still have a series of slides. So for example, one thing that is useful is, for example, to compare a protein tree and a DNA tree, like we did for trichophyton. And this is the tree that we, yes. Mm-hmm.
Look, do you then visualize them with ITOL, or what do you use for the trees?
ITOL.
Yeah, ITOL. That's what
yes,
I said.
yes.
It's ITOL. Yeah. Okay.
Mm-hmm. Yes, it's all the actually all the tool, all the trees are ITOL, and to import it in ITOL, and it works. So I'm sure that the format is the good one.
Yeah.
And
okay.
You will see also at the end of this presentation, you have a metabolic part and an INI part where you can incorporate matrix immediately to ITOL. But the only thing is that ITOL is not free. It's not very expensive, but it's not free. So I think you can also use, for those who want, use Fig3, for example, or something else.
Yeah. Okay.
This is a tree that we compute on DNA. For example, you have the DNA bootstrap here, and you have in B a tree based on codon 1 and 2, and a tree based with a partition different on codon 3. And you can see that the topology is the same. And this is why I say that this tree is we are quite sure about the result of this phylogeny. The last tool on the phylogenomic part is something that has been used for ULC. So the multi-locus phylogeny workflow is a phylogenomic aspect because you use multiple locus. When you do an SSU RNA phylogeny, frequently you lose phylogenetic resolution because of the because for single gene the resolution is less accurate than for multiple locus. And this is what this tool OPRER do. It will build a tree based on ribosomal protein, so multiple locus, and it will download this tree. To build this tree, we download the RefSeq or gene bank according to one taxonomic group, and then he will force the SSU RNA phylogeny according to this tree. So it will constrain the SSU phylogeny according to the ribosomal phylogeny, and the SSU that are not present in for example, in the genome, because you have something that is not sequenced, will be placed with higher phylogenetic resolution. That's what OPRER do. OPRER is currently not integrated in the pipeline because it's a separate project, but I will incorporate it later. The advantage is that you can easily, in one command, have an overview of all the strains that you have in your collections. So for culture collection, I think it's a tool that is really interesting. For example, if you want to make to sequence a new batch of genome, and you want to know if you have close representative, then you can just run OPRER. It takes 2 or 3 days to run, and you will have the results, and it will guide you to maybe in the selection of exotic strain or something like that. as it's not integrated yet in the pipeline, I will not give you an overview of that. It will be present later in the GitHub. We come in the final tools. We still have 2 or 3 tools. A tool based on average nucleotide identity. Here is a very simple tool because you provide a series of genomes, you compute any distance, and the tool will produce for you a heat map that is organized according to a list. So this is why I said that it is the matrix who produce this heat map can be also, as it's based on the list, can be incorporated to ITOR to produce a heat map in ITOR just beside the phylogenetic tree.
Luc, does it also provide the values, or is it only the heat map? Also values, yeah.
I will show you. Yes, the values are also provided.
Yeah.
I also add something a little bit more, so I will immediately go to the result. Let's see the job after. So you have the heat map in terms of PDF, and you have also the FastINI. So it's run by FastINI. You have the FastINI matrix pairwise, and also in the INI close match. If you go there, you have all the genomes that you provide in the list or in your directory. It should be the same. You have something like that who provide you the closest genomes. So you have yourself at beginning and the closest one decreasing. Okay. Maybe I will mute you.
Yep.
Yes, that's it. Don't hesitate to come back. And yes, so that's the result of this tool. I think that the close match is also something that can be used to define a single gene content or something like that. The job file is quite easy. You have to provide a directory for the genome. Here I can name it genome, and you have to provide a list of files. And actually, it's all the genome provided in the genome directory should be present in the list, and the heat map and the INI matrix will be ordered according to this list. That's for the INI. So you can work also for eukaryote and prokaryote here. But if you're, I will go show you that in the GitHub. Below 80% of similarity, the INI value are not computed because it's not recommended by FastINI. They tell us that below, I think it's 78%, and below that it's not computed. Okay. No, I don't have that here. I should add it. So I have a heat map, and so the INI that are below 80% are shown in white in the heat map. But I will add that in the documentation because it lacks. Before going on the, I think it's the final one. No, two last one. I still have this one. So I show you the multi-locus maximum likelihood, and we have a lighter version of that, who is the single locus maximum likelihood. So if you provide,
sorry. Look, maybe Ilse can also say something, but I know that there are several algorithms to do the same as ANI, but with a slightly different method, like the digital DNA homology and different methods. They are called, they are in a kind of category, the OPRER.
Yep.
So is it because ANI is better, or I don't know?
No, it's more because ANI is the most used. So
Yeah.
it's used in the GTDB project, for instance. And so I think it's make the consensus in the community. But I haven't compared to MASH or to other tools.
Yeah.
It might be something to do.
I think indeed fast ANI is what they use here in the lab to get a quick overview of the relatedness between your strains. Then for final publication, some other ANI values may be more interesting to use, especially for taxonomic papers. But yeah, there are several publications where they compare different ANI tools. And so, yeah, digital DNA hybridizations is also used, but the most used ones are ANI. That's true.
If you have a review paper or something like that to send to me, I can have a look and see if I can add another option and tell, well, we use fast ANI by default, but maybe you can use something else because the output would be the same.
I have a review, but I think it's already from 2018 or so. So it's not the newest one, but there they compare different values. Yeah. I will send it to you. Yeah.
Thanks. I will have a look.
And yeah, on these topics, I've recently read a paper. I should have probably sent it to you. That or not. It's not a paper. I will look. But saying that in this genome alignment used, for example, by Huguenots and so on, they take out a lot of positions from the alignment, so that in fact they build their phylogenies and groupings based on quite a small number of positions. And here, is there something that is responsible for a selection of some position of the alignment, or not?
In INE, no, it's genome wide, and in terms of phylogenomics, the only selection is the core genes, but we don't have a specific. And in OPRER, yes, we made the alignment on ribosomal proteins, but it's the only tools where we select the. OPRER is the only tool where we select specifically the proteins for the alignment. So we don't. I know what the approach of GTDB is quite similar to GENERA-Training. It's the same team, so it's probably related to marker genes like in GENERA-Training, and then made the alignment on that and the phylogenetic placement on that. I'm not really aware of that, but I think I read something like that. And also we use GTDB in the next workflow. So yes, also GTDB can have that. But I think all these results should be confirmed. INE and GTDB should be confirmed by phylogenetic inference. So I would say that GTDB and INE are like preliminary result that you have to combine with something much stronger, like multiple corroboration on the core genes in DNA and proteins. So I just forgot to mention that we have another, I will not show you because it's exactly the same thing as the multi-locus phylogeny, but it's the single locus. So if you provide your orthologous groups for the phylogeny, what you will have at the end is a phylogenetic inference per orthologous groups. So for the core genes, for example, if you want to look which gene is the more similar to your concatenation to find the marker genes is what you have to do. And so we still have, yes, the GTDB one. GTDB is, so for INE, for GTDB, I put immediately the link of GTDB because the workflow is really simple. It's just to help you to run it and to point correctly on the database, on the cluster, because the only thing that the program do is running GTDB. So I will not give you an overview of that because it's just exactly the same as the other one. You provide a directory with your genome and you will have the GTDB output. But just to remind what is GTDB, GTDB will take your genomes and point on another taxonomy. So you have the NCBI taxonomy and you have the GTDB taxonomy, which is slightly different, and who delete the unknown genome from the phylogeny. So it means that you will always point on something that is known. So it might be useful to reduce the amount of unknown in metagenomic dataset. This is the purpose of GTDB. So the tool Metabolic is the last one. And you have two possibilities with this tool. If you have eukaryote, so you have to provide, if you are eukaryote, you have to provide proteins. And if you use prokaryote, you can provide the nucleotide. But if you want to use the functional part, you have to provide the proteins. Functional part works with Mantis. So what it will do is that for each gene, it will run on different databases like KEGG, NOC, PFEMS, and with output you the consolidated functional meaning of your sequence. That's, for example, if you want to know what the specific genes do, you can put the specific genes and launch it with metabolic.nf in functional mode. If you use prokaryote, you can run the modeling part. The modeling part use KEGG pathway and try to infer presence absence of KEGG pathway in your genomes. So I'm showing you immediately the output of that. So the output of KEGG pathway is, of course, you have the different metrics, but you also have a heat map of presence absence. Black is presence, absence is gray. And you have here the different KEGG pathway. For example, you can know that this KEGG pathway, glucosamine biosynthesis, were present in all of your genome, but not in these two one. And by opposition, you have something present in all, yes, in the same way you have something present in all of your genome. Here you have the difference. So that's a way to see if you have a metabolic pathway present or not in a specific part of your analysis, and to go into the KEGG pathway based on the identification in the KEGG pathway to try to infer if you have, for example, if you have a synobium that is specific to Arctic, do you have a metabolic pathway present in this synobium and not in the Antarctic, or not in the closest representative that are not called cyanobacteria? That's what the metabolic modeling do part. And I put the link to Envio because it's a workflow developed recently by Envio. And the only thing I do is print the heat map in ggplot2, but and make the link with the name. So it's very easy to use also, because you have just an in file with your proteome or your genome, and you should specify the mode if it's functional or modeling part. Of course, if it's functional, you should provide the protein, and if it's modeling, you should provide the genome, but only if it's prokaryotic. And you should also provide a list, you can provide a list to order the heat map. So it's more easy if you can order the things that are related in terms of phylogenetic position together than completely mixed. One thing that I will add for this workflow and also for average nucleotide identity is the possibility for the list to provide a phylogenetic tree. So to automatically build the phylogenetic tree based on the list based on the phylogenetic tree. And that's all. That was the last one. It was quite long, but it's the last one of the 14 tools. So now you have a good overview of what we can do when I'm telling you that it's genome from phylogeny and more with one command line workflow. That's really the summary of the Genera toolbox. Of course, what I would like to do is to publish this toolbox. So I think it's a work that I would like to do in the 2 next months. So please try it, and you are the beta tester. So if you find something not logical, tell me, I will modify it. So any feedback is welcome also on the help, on the how to use it. So I will add a specific part for the non-Genera users. And one thing also that would be kind for you to do is that to modify, to read the documentation and to modify, for example, a typo, because I'm dyslexic, so I cannot see it. Even if I'm trying to look it there, I can see it. So if you can modify that or tell me when you find one, it will really be helpful also. And of course, any add-off tools will be nice. And of course, all the people who participate will be integrated in the publication, of course.
Yeah.
So I don't know if you have questions on that.
It was a very nice presentation, and compared to the first training that I received, I think it's really clear now how to use it. So I think the combination of this presentation together with the help and the guidelines in GitHub should make it feasible to go through a lot of the steps. So, yeah.
So don't worry if you find something that doesn't work. I already test all the pipelines and other people also, but as I said, just a different naming of a file can crash the thing. So this, how we will make it more resilient to naming is by testing it, of course.
Yeah.
So I still have a small part that some of you know is quite short. You see, it's just a series of slides to show you how to connect to NIC 5. So of course, I already mentioned that you have to manage your space and clean it. But you see that when you need 3 passwords to work. That you need to have one for GitHub to interact with me and with other people. You have the VPN if you are not from UDH University, and of course also if you are outside from the university, if you have UDH people, and something to pass the SSH gateway to come on NIC 5. So the VPN is really easy. If you go in the table of content, connection 5, and you have the information on the VPN. So you right click, I think you will have to pass your username that has been sent by the university to you, by the CG. And you will come on this page. You can put it in English. And you have to download the VPN, the configure VPN for Windows or for Mac. If you are from Linux, you have to read the step below. So once you want to connect, always activate your big IP client. If you have a problem with that, you can contact the CG who will help you. For the SSH, you have 2 possibilities. You are from Windows, I think it's the case for most of you, or you are on Mac. We'll see the Mac at the end. So for this SSH, again, you can go on SSH connection from Windows user, and you will arrive on the documentation of the CC. Here you have a link to go to MOBA Extern, and you have to go to download part, select download now, and take the portable version. The portable version is really what you need to take, because you don't have you don't need to. It's very easy to install, and you don't have to ask the permission of your sysadmin if you need it. And then you have a series of steps. You double click on, you download it and you put that in your document. So the portable version. When you double click on mobile extern, it's just a simple execute file, so you don't have to install it. And you click on the session part while having your big IP client, so your VPN, activated. Then you will, once you click on the session icon, you will come to this, and you have to put the remote host. This is this, and you have to specify the username. This is my username. Of course, you have one that is specific to you. When it's done, you take the port 22, you click on Advanced SSH setting, and you can click here on you check that it's SFTP protocol, and that you point on your RSA key, rsa.cc. Then you go on network settings, and you specify here the gateway, jwcc.ulh.be, still on the port 22. You specify your username here. I forgot to put an arrow. And you specify the path to your rsa.cc that has been sent to you by the CC. This can be this image or this image if it's new. Then you click on OK, and we will prompt something that will ask you your passphrase from the CC, the one that has been asked to you once you built your SSH key. Note it and don't forget it, because anyway we have to ask you to renew your account. So that's not. It's just more easy if you can keep so note it on a piece of paper and keep it. And once you have done that, you are immediately connected on the cluster, just as it has been that I show you in the morning by SSH NIC5. You arrive here. If you have a UNIX, so a Mac, that's more simple. You run this series of commands while pointing on the RSA ID.cc that has been sent to you. So you make a directory called .ssh, you move the ID in .ssh, you change the permission, you generate your key, name pub, then you do something called nano, as I show you, and you put that into the config file, and you specify your username by your username, and then you again chmod that, and you can make an SSH NIC5. It will ask you also your passphrase. That's all. And so if you have a problem with that, you can ask you can ask help to the CC, but really I think that all the new users from the CC use this mobile Xterm documentation, and it works fine for them, so it should be the same for you. And yes, and then you have the information on NIC5 and infrastructure of everything that I already showed you. So that's it for me. I don't know if you have any questions regarding the training or the connection.
Luc, can you share also the presentation of today on the GitHub? Is it possible?
I will try. Maybe it's very big, so if not, I will make a link to download it from the NCB, from the Mercy, a link from ULH. So I will send it by email or something like that. Okay. But it will be available.
Yeah, I also have a question. So now today it came clear that I have to work on the global scratch, but I think I just worked on my home. So I'm not sure what I can remove from the home, what should be in there, what shouldn't be in there.
I will show you. So
yeah.
if you arrive here, so you can see that it's not a problem to work in your home, but you can see that the space is limited,
Yeah.
and that you also have a series of files quite limited. So at the moment, what will happen is that you will not be able to run anything new, and you will just contact the CSE because you will not understand what happened.
Yeah.
And so the best is to have nearly nothing. And if you want to move something to your global scratch because you think that you want to keep it, you just do that. For example, I want to move, let's say, output to global scratch, and I can rename it.
Yeah.
Voila. And there you will not have here anymore. And if you go in global scratch, I think that you, yes, of course, that work if I do that. And yes, it is there. Of course, my directory was empty, so it's still empty, but you can move things to the global scratch and then continue to work in the global scratch.
Yeah.
And
okay.
be sure to modify correctly the symling within your file, because the file you have in the job file or in the Nextflow configuration file, you must specify the pathway, pwd, and read link, and it will continue to point on your home if you don't modify it accordingly to the scratch.
Yeah, I have to pay attention to that. Okay.
Just I've sent to you all an email with a presentation of Ramon Rossella, who is telling that the GTDB in fact use only 5,000 positions, so he's losing 90% of the positions for their work, okay, because they have missing sequences. If you take all the genomes, I guess it's a bit like a patchwork, and so they keep only 10% apparently.
No.
Okay, that's interesting. I will read it. It has been that when we use GTDB, it's important to maybe to correlate that with Busco phylogenetic placement or with checkm placement to be sure that is correct. Okay.
Yeah, I
so thank you.
We want to thank you, but I think we will need quite a bit of help in the coming weeks.
Yes, I know. But I think for most of the collection, there's already one people who manage that. For example, Benoit can easily run that in ULC. Elizabeth has no problem also in EHEM. I think that Wim should run that easily, and Oren also for ITM. And I think that MULC, I think I will maybe have to provide some help. And Ilse, I think that the postdoc that work with you already can do that quite easily.
Yeah.
I want to say that Benoit is finishing his PhD and is not happy at all when we ask for some help.
Okay, I understand.
And he's not paid. He's doing
that.
something else. Yes.
I'm paid for that. So if you need help, I can provide help at least until the end of my contract within June. So run it, try to make things. I don't know if other people from ULC can follow the training when it will be online, but maybe Kim or I don't know.
She might be.
I will also provide a lot of help to Marcello, of course, because I think Marcello is not aware with bioinformatics, and so I will. Don't hesitate, Marcello, if you need help to make a lot of short Skype with me, and so don't get stuck. Let me help you.
Probably I will need to ask you many things. I take some notes here, and I will mail you or try to make a Skype to solve them. Okay.
Okay. Sure. Great. So use the tools, come back to me, and don't hesitate if anything is unclear. I try to make most of the things clear, but of course, to make and don't try to make a very long documentation so that you can easily find information in it. But if something is lack, and I think it will be the case, of course, don't hesitate, and we see together how to add that and to improve.
Yep. And look, I added the review paper on all ANIs are not equal in the chat.
Okay. I try to find it.
It's the last thing. Yeah.
Okay.
It's too big to send by email, is?
I can also send it. Yeah, I sent a DOI, so you can find it easily.
Yeah, but the chat is gone.